anybody's wondering, we run a title sequence beforehand as we're running right now. It's very short, like 2 minutes or a little less.
So before we get into that, we'll do a business meeting after Steve talks, and it'll mostly be about astronomy days or event at the end of the month, and that's all good.
Seems like a long time.
Welcome to tonight's meeting of the Raleigh Astronomy Club, January. Our speaker tonight is Dr. Stephen Christensen, who will do a talk for us on black holes. Steve is a theoretical physicist, a research physicist at the University of North Carolina, Chapel Hill. He's also a Raleigh Astronomy Club member and a member of the Chapel Hill Astronomy Club. So without further ado, I'll turn it over to Steve.
Thanks, Brian. That's not good. All right. Stay away from that. I realized driving over here tonight that it's been 50 years that I've been doing this kind of stuff. So maybe that's a little too long, but it's fun. So, all right. So I'm going to talk about black holes, and in the end, I'm going to talk about the question: are they really black? And I'm going to do a bit of historical discussion, talk about some of the people that are involved in the whole subject, which has been around for quite a while now, and basically try to discuss some of those questions that we have up there, and then look at, are they really black? That famous picture of Einstein writing a very simple form of Einstein's field equations on the blackboard, which is something you see all the time in various websites and whatnot. Well, if you know anything about black holes, you've heard this kind of statement before. Black holes are a region of space where gravity is so strong that nothing, not even light, can escape. Well, that's the standard definition that everybody uses. But this is a very limited definition of a black hole, and it's probably even incorrect. So we're going to get into that a little bit toward the end of the talk here. The first notion of a black hole probably came about this time in 1783 with a reverend in England, Mitchell, and he wrote a paper that was published in the Philosophical Transactions of the Royal Society. And he was wondering what would happen if a particle of light, because they thought of light as particles back then, were to try to escape from an object that was very, very massive, using Newton's laws and that sort of thing. And they realized that at some point, the escape velocity to a very, very dense, very massive object would be greater than the speed of light, which meant that light couldn't escape from that object. And so he published that, and it kind of just sort of hung around for a while until this fellow came along, who was much more well-known, Laplace. If you know any physics or mathematics, you've heard Laplace's name. And he actually considered this idea in a mathematical way and made a mathematical proof of the notion that light potentially could not escape from a very massive object. But not much happened with this idea for quite a long time until our friend Einstein came along and wrote down his gravitational field equations in the early 1900s. And that equation I've got right there is the gravitational field equations. And basically, what it says is that on this side is the geometry of space-time in terms of things called the curvature tensor. This is called the Ricci tensor. But these all have to do with the curvature of space-time. That's the famous cosmological constant that's become very interesting lately. On the other side is whatever matter there is in space-time. Stars, gas, whatever, light, any kind of energy or mass or pressure or anything like that. This object on this side is called the stress tensor. And it contains all the information about matter in the gravitational field. And so what this equation really means is the space-time geometry is equivalent to the matter and energy. They interact with each other. So the matter creates a gravitational field. The gravitational field affects the matter. So there's this very, very complicated set of 10 nonlinear coupled partial differential equations, which cannot be solved analytically in any way. If you know anything about differential equations, these are about as hard as they can get. The other equation that's important is this equation having to do with the stress energy tensor. And this is the conservation of energy momentum. And these equations are written in this way, and these objects are called tensors. Now, those of you who know mathematics know what a tensor is, but basically they're written in this tensor form because these equations become invariant depending on, they don't depend on which observer is doing the experiments. You don't want your theoretical ideas and your equations to depend on who's doing the calculations. So when you write something in these tensor forms, that goes away. Everybody would agree that these are the equations that you get no matter how they're moving, no matter what kind of gravitational field they're in, no matter what kind of matter they're in. This is what they would come back up with. And these equations have been tested a lot since they came along. And so far, nothing's come up that shows that they're not correct in incredibly accurate forms in all kinds of different kinds of tests. Well, very complicated equations. Initially, no one really knew what to do with them until this fellow came along, Schwarzschild, in 1916, shortly after Einstein published these equations. And he said, okay, we've got these complicated equations. How do we make them simpler? So he said, I'm going to try a point particle, say here, of matter of some mass m. And I'm going to see what the gravitational field of a simple point particle with no other matter around it at all is. And if you do that, your equations become very, very simple and easy to solve analytically. And he found a solution which looks like this, which has to do with the mass of the particle that's down here and the radius away from the particle. And this has to do with the spherical symmetry of the object. That's less important. And of course, when you look at this, you start to see that as the radius goes to 0, these things blow up. This one in particular blows up and goes to infinity, which is not very reasonable. And if the radius goes to 2m, something else happens. This goes to 0. So weird things happen there. So what they found is that there was this radius around this object here where light couldn't get out. Any kind of particle of light sitting here trying to get out through that radius couldn't do it. And that this point there had an infinite density or infinite energy, which we know is nonsense. But so the solution is kind of nonsense, but it's also very interesting just to see that this kind of thing could conceivably happen in the world. No one back then believed they really did. It's just that this was a solution, and they had to take it seriously. Because if you couldn't take it seriously, there might be something wrong with Einstein's equations in the beginning. So, and initially, a lot of people thought that the equations just couldn't be right when there were solutions like this. Well, then people started really getting interested in things like stellar collapse, what happens when a star collapses, when its energy burns out. And this fellow came along, Chandrasekhar, and he found that if you reached a limit of like 1.44 solar masses, that when the star started losing its internal pressure, it would start to collapse. And it would collapse into something that was a white dwarf star. And so this is kind of a prediction that came around. And Chandra is, I knew Chandra, he's gone now, but he was at the University of Chicago for quite a long time. Absolutely lovely man. Very modest, very quiet, kind of shy. But he was the guy that you went to if you had a question you couldn't answer. You were doing research and said, I don't know where I'm going with this. You go talk to Chandra, and he would set you straight. And so, a wonderful guy. This is all back in around 1930 when he did this. So there was some notion that some weird stuff, weird objects were going to occur when a star's energy was started to burn out and it started to collapse. So a little further on, Oppenheimer came along. This was prior to the Manhattan Project, prior to the atomic bomb, prior to all of that. And he was at the Institute for Advanced Study in Princeton, working with Einstein after Einstein got there. And he and Volkoff and other people began to understand that the white dwarf star wasn't the end-all of the collapse of an object, that it could move even more dense as the star initially was bigger and bigger. The more mass it had, the more collapse it would do, and the more dense it would get in the end. And he came up with something called neutron stars, when protons and electrons basically combine together to make neutrons when things get really smushed down a lot. And then they realized in 1939 that even a neutron star might not be enough, that the forces that would keep all these neutrons together weren't enough to stop a collapse if the mass was big enough. And that's where the notion of a black hole came along. They didn't call them black holes. That was due to, in the 1950s, by John Wheeler, who was also at Princeton. And so they realized that there was yet another place below neutron stars where things could go. And because of the Schwarzschild solution, they believed it was an object like a black hole. Whether it was exactly a black hole was not clear, but something like a black hole. Well, after the war, I mean, the war stopped everything. Everybody worked on the Manhattan Project and other things. But after the war, all these people started to do physics again. And they started to be interested in gravitation and quantum theory and that sort of thing, and to see what they could do to unify these things and to understand them better. So they started looking at what happens when you quantize electrodynamics. And Feynman and Schwinger and others came along, Dyson and so that's Richard Feynman, who everybody has heard of, and that's Julian Schwinger. Feynman was at Cornell and then Caltech, and Schwinger was at Harvard. And they got together in these meetings in the 50s. And there you see Wheeler and Feynman and Schwinger's in there too. And they had this very famous meeting of these guys together, worrying about how to quantize gravity. Quantum electrodynamics worked. It predicted a lot of things which were experimentally verified. What about gravity? Can you put quantum theory and gravity together? So they started thinking about that. And in 1957, in Chapel Hill, these guys all got together at a very famous meeting that was chronicled in a Reviews of Modern Physics journal, all the papers that were published. And they said, what do we do to try to figure out gravitation and quantum theory? And so they came up with some ideas. This is Bryce DeWitt, who was a student of Julian Schwinger at Harvard. And Feynman and Charlie Misner, who is at the University of Maryland now, were students of John Wheeler. Wheeler was an incredible teacher, an incredible advisor. So, you know, to have men of this caliber as his students says a lot about him. He was an absolutely wonderful man. I spent some time with him in his group at Princeton back in the 70s, and just gloriously wonderful man to work with. Schwinger was scary. He was so brilliant, he was scary. He could give a lecture on a blackboard and starting in one corner and ending down the other corner, and just perfect equations all the way with perfect explanations of everything. An astonishing man. And Bryce, who was my graduate advisor in Chapel Hill, I'm putting these little UNC Chapel Hill logos on here to show that a lot of these people have local connections in one way or another. So Bryce was also very precise and amazingly brilliant fellow. And they all got together in 1957 to investigate these things. And one of the things Charlie did was to say, we need to use computers to do this kind of work. We need to use numerical simulations because we can't solve Einstein's equations in a perfect analytical form. We need to use computers to do approximations. And so in this 1957 conference, he proposed that computers be used to do this. Well, back then, computers weren't good enough to do anything, really, in this regard. So those ideas kind of floated around for quite a while, really about 20 years before when the computers became available. The other amazing thing that happened in 1963 was that another solution, another black hole solution came along from Roy Kerr, or Kerr, depending on how you want to pronounce it. And he came up with another solution which is much more complicated looking than the Schwarzschild solution I showed you before. And what this was a rotating black hole. We know that most stars rotate. They don't just sit there as spherical objects, they rotate. And so he found a solution to Einstein's equation after an extremely tedious calculation, which in 1963 was extremely tedious, which nowadays can be done in a few minutes on a computer, but couldn't back then. And he found a solution where you have a region around the black hole where things not only can't get out, but can't stop from rotating around the black hole. So things that get into this outer region here are forced to go around it. They can't just sit still. They don't just fall in straight. They have to rotate around. And this is a very important notion because later on, when we started to see things like black holes in outer space, we saw these disks of matter around it. And that was a dead giveaway that what was inside here was something like a black hole or literally a black hole. So that's an incredibly important discovery. Since then, there have been others, charged black holes and black holes with magnetic fields, that sort of thing. Now, in the 60s is about when I got into this, doing this stuff, and I was just going to show you, talk about some of the people and some of the inspirations if you're interested in going back to look at these things. There's Einstein in Princeton with Tominaga, and that's Johnny Wheeler. And then here's Einstein with Bargmann and Bergman. This is Peter Bergman. And then there's DeWitt again, who was at Princeton for a good amount of time at the Institute there, and also at Chapel Hill. And then these books were the kind of things that every young theoretical physicist who wanted to do gravitation had on their bookshelves. There was the space-time physics book by Wheeler and Taylor. There was this book by Bryce DeWitt. And when I first got that book, and I read through the first chapter of it, I understood not one word. And that was the simplest chapter. And so I said, I've got to know this guy, because he knows things that I can't even imagine exist in the world. And fortunately, later on, I became his graduate student. But this is an astonishing book, but very, very difficult book. This is Peter Bergman's book, which was one of the very first technical relativity books that was published back in the late 50s. And I got this book when I was in high school from a local college professor, and I read through it from cover to cover over a summer and found typos in it. And so I thought, you know, this poor guy, he's got typos in his book. So I sent a letter off to this guy saying, you got typos in your book. And you know, dumb high school student. And so about a month later, I got a letter back from him. He says, yeah, I know the book was published 15 years ago. We kind of know where the typos are. You know, and I felt like a complete idiot. And furthermore, I didn't know who this guy was until I found out later he was one of Einstein's assistants. And so I said, I hope I never meet that guy, because if he remembers me, I'm going to be terribly embarrassed. Well, fortunately, I did meet him 20 years later, and turned out I couldn't stand him. Because he was Einstein's assistant, he was very arrogant. He thought that everything he said was correct. And he did not like anybody who would question him. And so I didn't mention to him that I was the guy that was sending the letter back. Anyway, but this actually is quite a good book. It was a really good book for learning the details of relativity. Then there are these other books, this book, Gravitation. This is another book by Bergman, which was a more popular level book. which was also very good and very interesting. So, I mean, I could still actually recommend, this book I don't recommend unless you're incredibly serious, but it's an amazing book. These other books are still relevant, I think, even now, all these years later. Okay, well then in the 60s, these two guys came along and threw a monkey wrench into everything. Everybody wanted to understand the notion of the singularity inside a black hole. Nobody liked the idea. They wanted to know what could we do to solve that problem or to understand it more. So Roger Penrose, who was at Oxford, and Stephen Hawking, who was at Cambridge, got together. Actually, at the time, Hawking was not at Cambridge. He was working with Dennis Sciama in Oxford. And if you see the Theory of Everything book, Dennis and Roger play a role in this movie about Hawking. And if you're interested in physics at all or interested in Hawking, it's a really good movie. It's accurate with regard to Hawking and his wife, I suspect, because it's based on Jane's book about that. It's probably inaccurate in terms of Penrose and Sciama and these other guys, because the actors who play these roles in the movie don't look anything like or act anything like the guys did in real life. I mean, Roger is kind of an impish guy and funny and just not and interested in lots and lots of things, and he doesn't come across that way in the movie. But you wouldn't know that if you didn't know them already. So it's well worth seeing. And what they came up with was the idea that no matter what kind of matter you start out with in a big bunch of matter that starts to collapse, it's always going to form a singularity, a mathematical singularity. And the only way to hide that mathematical singularity, that infinity that's inside the black hole, is to put a horizon around it where you can't see inside, where light can't get out and matter can't get out. So they did that by looking at this equation down here, which is another equation I'll throw in here just to show what they look like. Another tensor equation called the Raychaudhuri equation, which defines how matter falls together in a gravitational field. And so by doing a mathematical analysis of this equation and other things, they figured out that things had to collapse into singularities. But they always had to be hidden so they wouldn't cause a problem in the universe. So that was a big deal. Question?
So did Hawking's had the theory of the Hawking radiation?
I'm coming to that.
Is that next?
It's coming.
Okay.
Yeah,
Well,
in a bit of detail. Yes, it's coming. Yeah. I go.
You're talking about. I'm not familiar.
Oh, okay.
I'm not familiar with their work, but intuitively, wouldn't you expect this result? Was this surprising, or what was the alternative to what they found, I guess?
Because they did it very generally, in the sense that they didn't care what the matter was that started out with, or what the boundary conditions was on that matter. It was possible that if the matter was rotating really fast, or if something else was going on, they did a very general proof that almost no matter what form of matter you had, that ultimately it would collapse into something like this, and that hadn't been done. Okay, and so that was the thing. No one had done, and if you read the papers, they're incredibly detailed mathematical proofs. They don't even look like physics papers; they look like math papers. Okay, because they're really analyzing in detail this equation and the boundary conditions on that equation and what would happen to it. And so that was a big deal. And that's what Penrose was already famous. That's what made Hawking famous. Frank?
Some of those books you showed back on,
Yeah.
you said 60s inspiration. Were those made earlier than 1960?
Somewhere, yes.
Wonder how much earlier?
In the 50s, mid to late 50s.
Actually, I bought an astronomy book at the Asheville auction that was made in 1897.
There wouldn't have been any relativity books then. 1905 was the first time. And Einstein had written very famous books back earlier than that are still worth reading. The ones I show there are a tiny bit more technical than Einstein's books are. Okay, so anyway, this is when Hawking and in particular Hawking became quite famous, and also because he's in a wheelchair and all that. But back then he could speak and get around, and it was quite different. The movie shows that in an interesting way. Okay, then in the late 60s and up to 1974, there was another revolution in this where people started to really take seriously what happens if you try to do quantum mechanics when you're in a space-time that's curved, or when there's a strong gravitational field, or around a black hole, or at the beginning of the universe, that kind of thing. And these people, Leonard Parker, who's down here, who's in Milwaukee now, at University of Wisconsin-Milwaukee, but was a postdoc in Chapel Hill, Jacob Bekenstein, who was at Princeton, and then Hawking. These three guys got together and they started to understand what would happen if you had a quantum field around a black hole. And they realized that because the way the quantum fields work in a vacuum, you get particles being produced and then reabsorbing and being produced and reabsorbing. If you have a black hole or a strong gravitational field, some of those particles can escape from the other one that's being created and go into the black hole, and some can go out from the black hole. So it looks like the black hole is putting off some kind of radiation. And so these guys, I mean, it's mostly called Hawking radiation, but it really should be called Parker-Bekenstein Hawking radiation, because Hawking's work was based on the work that Leonard and Jacob did. So this became a big deal because it finally gave us some notion of how to unify quantum mechanics with relativity and gravitation, but also maybe some tests you might be able to do. And then the whole notion that a black hole might give off radiation and shrink down and kind of evaporate away was a big deal. And of course, Hawking became very famous back in the 70s because of this, partly because of this work, but partly because here was this guy in a wheelchair who was doing this amazing stuff. And so there was a lot of press hype about it. In the world that I existed in during this time, he was another physicist, a nice guy and very smart and fun to be around, and had a good sense of humor and all of that. But he wasn't any different than any of these other guys. It's just that the newspapers got a hold of this and hyped it up. And in particular, the people who were around Stephen liked that hype because it hyped them too. So that was mildly embarrassing, but also interesting to watch. Then came 1972, and Cecile DeWitt, who was also at UNC Chapel Hill, because she was also on the faculty there at the time, along with her husband Bryce, they organized a conference in the French Alps at Les Ouches, which is near Chamonix in the French Alps. Beautiful, beautiful place. And they would have month-long summer schools, they called them, where people would get together, both professors and students, to talk about some given subject for a month in the French Alps, which is very conducive to that kind of thing. And then here's a picture from that summer of '72 conference that I think I took, but I'm not sure. There's Kip Thorne, who we'll talk about some more, who was also a student of Wheeler's. There's Bryce DeWitt, who was my advisor. And they're, after one of the lectures, they're talking with the speaker in this lecture hall at this school. But what happened here is that Hawking and Bekenstein and Parker and I and all the DeWitts and Thorne and everybody else were all there. And we could all get together and start talking about what the big issues were in black holes at the time. This was before black hole radiation. This was before a lot of these things had happened. It was just beginning to happen. And it was this conference, I think, that started everything going on all future research that's still being done today. And a book was published on that, which you can still get, which is quite amazing. It has long lectures by Hawking and other people. And there are lots of other conferences have been held there that Cecile and Bryce organized over the years. So '72 was a big turning point, just like '57 was. And both connected in one way or another to UNC Chapel Hill. All right, so '74 was when the Bekenstein-Hawking radiation really started to get going. And the notion is that you have a star or a black hole, and you've got particles being created outside the black hole. Sort of negative energy particles fall into the black hole. Positive energy particles go streaming out from just outside the surface, basically. And the negative energy going into a positive energy object causes the mass to decrease, so the black hole shrinks. And as the black hole shrinks, the gravitational field around it gets stronger, so it produces even more particles and more stuff going out. And so as it shrinks down, it gets brighter and brighter and brighter, mostly in gamma rays and that kind of thing. And then eventually poofs out, whether it's an explosion or something else. You know, no one's ever seen this happen, but this is what would be predicted to happen. And so really small black holes might get very hot and explode in gamma ray bursts. And people are beginning to understand there were such things as gamma ray bursts, so maybe these were exploding black holes. And so when that happened, of course, the world went pretty crazy for Hawking at that time, because this was very science fiction-y and very cool. And also something that might be tested that would help us understand quantum theory and gravitation. Well, this is kind of where I came in the early 70s. So I thought I'd tell you why I'm in here. That's me. I was at UNC Chapel Hill for a semester before I went to Texas, when DeWitt left Chapel Hill and went to Texas. And there I am. This is at Imperial College, and that's the Albert Hall in London. And there's Hawking sitting there, and there I am on the edge of this conference that we had there. My main interest was in quantum field theory and curved space-times, which had to do with trying to solve the problems of infinities that occur in these theories. And so I invented a way to do that to solve those kind of problems, and that's what I was working on when I was doing my PhD. And later on, my colleague Steve Fulling and I published this paper, which is called Trace Anomalies in the Hawking Effect, where we found a new way to derive the Hawking radiation. It was basically the second way. Hawking did it first, and then we figured out another way to do it, which I think was simpler. So we wrote this paper, which has become quite well known over the years too, and still being used, amazingly enough. Part of the problem that we discovered in doing this kind of work is that the calculations are incredibly difficult and very long. You get equations that are hundreds of pages long, one single equation. And this represents that I did for another talk. This is a piece of paper 30 feet long, one equation. And you might have, and you're doing a calculation, you might have 30 of these that have to be combined together in some fashion and manipulated. And it has to be done perfectly. You can't have a sign mistake. You can't have one of these indices on the tensor wrong if they're in the wrong position. The whole thing is meaningless. So you have to have perfection in this. And you can't have perfection doing it by hand. So I started writing computer software to do these kind of calculations, which is what this 30-page long thing was done with, and wrote a piece of software called MathTensor. This was back in the 80s now when we did this. To do these calculations for this took months and months and months to do by hand. And now those same calculations can be done in minutes with computer software and more accurately. So I kind of came in, my interest in software, which I still do, and my interest in physics kind of combined at this point to do these horrible, nasty calculations. And so that's sort of what I do and what I still do. In physics, at least. All right, so let's get into the actual subject of black holes, a little bit away from the history of it, and say, what kind of black holes are there? Well, we think there are three potential kinds of black holes. There's the standard black hole, which is formed from a star collapsing, or a bunch of matter collapsing, or some stars colliding with each other and coming together, whatever. Okay. Then there are these mini black holes. And then there are the black holes we hear a lot about, the supermassive ones at the center of galaxies. And they're all very different. And so you want to study each one and see what they say about the universe. All right, so where would you find these smaller mini black holes? Let's look at those. Well, probably at the beginning, at the Big Bang, it was possible that they were around. But they're probably not around now because, as I said, the black holes evaporate when they're small, and they explode. Now, you might conceivably be able to see some sort of remnants of these gamma ray bursts if you looked far enough back at the beginning of the universe. And I don't know that we've looked far enough back yet, It's possible that you might see some remnant of that, but it would happen so long ago, it had been so redshifted that you might not even recognize that's what you're seeing, unless there were a huge number of them. So the Fermi Gamma Ray Telescope looks for things like this, gamma ray bursts and whatnot. And then, of course, there was the famous story recently of the collider in CERN, the LHC, potentially producing black holes. And everybody was worried, and they were suing them to keep them from doing it, because if they produced a black hole, it would eat the Earth, which is utter and complete nonsense, because even if they produced these tiny little black holes, they'd evaporate so quickly, they couldn't absorb anything. So I think they're still looking. I mean, I think they're still hoping that they could produce something like that, because that would be really cool. Because if they produced one and it gave off the gamma ray bursts in the way that Hawking and Bekenstein predict, that would be an amazing discovery. And probably the only way Hawking would get a Nobel Prize, it would be for that to happen. Okay, the first really famous stellar-sized black hole that was discovered was Cygnus X1 in the constellation Cygnus. And what they did was they looked at this, and they got X-ray images of it. And they looked at the structure of the X-rays, and they said there's nothing that could produce this except the matter rotating around a black hole fast enough to produce energy of this magnitude. And so this was the first one that they believed was a black hole, and its mass was big enough, and it was dark. You couldn't see it, the star itself or the black hole itself. You could see the effects of the accretion disk. So this was really the first stellar-sized black hole type object that anyone discovered back in 64. Okay, I took 2 years ago, I guess, I took a picture of that area with my, I guess it was with a camera. And here's Eta Cygni in Cygnus. And if you look up here and you see that star there, it's got this really long name on it. And around that star is Cygnus X1. So it's possible to go and take a picture of it. You're not seeing the black hole, you're not seeing the X-rays coming off of it, but you can see where it is. And eventually I'm going to try to do a better picture, now that I know more what I'm doing, try to take a better picture of that region. So this is what they're looking for mostly when they're studying these kind of black holes, are these accretion disks of matter rotating around these things and producing X-rays coming off of it. And the Chandra, named after Chandrasekhar X-ray Observatory, does this kind of thing. And they've discovered a lot of these objects that produce a lot of X-rays, have the right mass. You can't see the central object. And so there are lots of these around in our galaxy that can be measured. And this is an example of one here. And that's an X-ray picture that they put of it. Okay. Now the other possible way to see black holes is their effect on gravitational radiation. Am I doing something wrong, Ian?
No, just for some reason we lost the slide of the broadcast. Pardon? Correct. How do I restart it from the current point?
Just hit play up there again. See if that worked.
Sorry, everybody.
Tell me if it's okay to go on. Well, Ian, I'm going to put all these slides online too, so people want to go look, they can look. Okay. All right. One of the most interesting ways you might be able to see a black hole is from its gravitational radiation, and that would occur mostly if you had two black holes colliding with each other. Now, if you look in the New York Times in the last few days, they're talking about gravitational radiation coming from the black holes in two galaxies coming together. And so you want to try to measure the gravitational radiation because that would be a dead giveaway that these are black holes doing this particular thing. So what they do is, what they've built now are these things called gravitational wave detectors. It's the so-called LIGO project. And they're enormous tunnels with lasers that shoot lasers back and forth in these big, long tunnels. And they measure how the light's fluctuating when they come back together. And they're putting these all over the world. Many of them are built now and just being tested and put together. And so once they have all these arranged, they can combine all the data from all of these. And when a gravitational wave hits the Earth, it causes the Earth to move in a particular way, to flex in a particular way. And so all these things all across the world can measure this motion. Now, a lot of the motion they measure are trucks going by and earthquakes and all kinds of other things. But combining them all together, because one in Japan and the one in Louisiana aren't going to have the same trucks, they're not going to have the same earthquakes, but they are going to have the same flexure of the Earth going on. So how do you detect that? Well, what they've done is they've made mathematical models of all different kinds of ways that black holes might produce gravitational radiation, or neutron stars and other things that could produce gravitational radiation. And they predict then what those things will look like. And then they take the noisy signals from all of these things, combine them with the mathematical predictions, and they can filter the noise out and see if this kind of signal is actually in the data from all these things. And so it's a very, very clever way of wrenching the data out of all the noise. And then, so there are instances now we know where potentially objects can do this kind of thing. And so we're hoping that these detectors will detect these gravitational waves. There are other ways to do it too. You can put satellites up in space and keep them very close to each other. And when a gravitational wave goes by, the satellites will move in a very particular way if the gravitational wave hits them. So it's a very, very interesting project. All right, here's some recent simulations, which I hope will play here, of two black holes coming together and producing. See, they have accretion disks and they're black holes, and they're putting off radiation in these beams that come out of their poles, and then they come together and they produce gravitational waves. And then this one shows the waves would look like coming out. And so you would look for these gravitational waves, which cause these motions of the Earth and other objects in a very particular way. And that would tell you that you've actually got gravitational waves. And that would be an extremely good test of Einstein's theory. Mike?
Is this what we would expect with the Andromeda Galaxy starting to head? I don't know which one's headed towards which one. Relativity says they're heading toward each other. I mean, there's no one heading toward.
Oh, right.
Yeah, okay. But yes, when it would depend on how they pass. If the supermassive black holes in the center of the two galaxies got really close, or if they started to come together and just started going around each other like this, eventually they would probably come together. But it might take billions of years for that to happen. But if they come bang on, that's different. But you can look at simulations of these things and say, now of course Andromeda is much bigger than the Milky Way, so the central black hole is probably much bigger. So you would say, okay, I've got a black hole of this size and a black hole of this size, and I can start moving them toward each other in certain ways, and then see what kind of gravitational radiation they will put off. But that's billions of years away. So it's better to look out in the universe, because there are lots of colliding galaxies out there to look at. Okay, and so the trouble is some of them are so far away that the gravitational waves that would come from them are so weak that even the LIGO detectors couldn't detect them. So you want something relatively close in the terms of billions or millions of light years, that kind of thing.
I had a question, Steve.
Yeah.
So the cross section for actual capture, are you relying on some sort of general relativistic drag to get these? Because they're going to have angular momentum relative to each other.
Yes.
Is there something going on that's going to make these guys actually drag and capture versus just kind of like two-point particles passing each other?
It really all depends on the initial conditions.
Because unless they're directly head-on, I don't see how they would ever actually.
Oh no, they do. I mean, it's known. I mean, just go look at some of the pictures of the galaxies that have already started to coalesce, and you'll see that they really are close enough that over time, or millions and millions of years or billions of years, as their orbits, they'll start to spiral toward each other. But it entirely depends. I mean, the two galaxies, the two black holes can just go right past each other and not capture at all. So you just have to, it's not always going to happen.
Okay. Yeah, I thought that was more of a hydrodynamical gas type interaction.
Well, it is.
Or is the black hole kind of stuck in the
galaxy? Well, the black holes are pretty massive, but they're also very small.
Okay. So they're kind of stuck right along with the galaxy.
Yeah.
Okay.
Yeah. Okay. Then, of course, we have supermassive black holes in lots and lots of galaxies now. Most galaxies seem to have these supermassive black holes in them. And that's proven mostly, I think, because of you can understand what the mass of the central object is relative to the structure of the galaxy. And it has an enormous amount of mass in a very small area, so it has to be a black hole type object. It also will give off radiation from its poles if it's spinning, and they tend to be spinning a lot. So you can look for jets of gas coming out of them, and lots of galaxies have that kind of structure. And so, we're pretty sure that most galaxies have a central black hole-like object and have a particular kind of structure. And just looking at a sort of standard place that you would look at in the sky at the Big Dipper area, there are all these galaxies that I marked, and probably many more, have black holes around them. M51 we all know, and M81 and M82 we all know all have central black holes in them. Okay, and then of course in our own galaxy we have the Sagittarius area. Sagittarius X1 is the central black hole, so-called, and we know a lot about it because we've over time looked at the stars that are in that area and looked at their orbits. And so by calculating the orbits of all these stars over a period of time, you can get some idea of what they're orbiting around and then get an idea of what the mass is. But the fact is there's this huge mass at the center, but you can't see it. So it has to be a black hole-like object. Yeah.
So have you, do you know of any more of the research that says that there's a correlation between a black hole in the middle, that each galaxy has a black hole in the middle of it, that there's some sort of relationship between the birth of a galaxy and the birth of a black hole?
Yeah, I think there's lots of ways to look at that. The first notion is that there were black holes that were formed in the beginning of the universe, and matter coalesced around them. Some about this, there were big, gas clouds, and the natural thing for them to occur long ago was to go into a black hole. But I don't think anybody really knows yet which of those things.
That's where they left it.
Yeah, it's left there still. There's not enough data yet, I think, to know what happened. I mean, as we see galaxies further and further away and see what their structure, older and older, I should say, what their structure is, then we'll know more about whether there were black holes there then, or whether that came later. So it's the chicken and egg, which came first, the black hole or the galaxy. And I don't think anybody really knows that yet. I'm a theoretical quantum field theorist, not an astrophysicist, so I don't know all the details about what's being done. Yeah. The latest thing is there was a gas cloud near the center of our galaxy that was heading toward the central black hole. And they were wondering whether or not that central black hole was going to do something to the gas cloud. Well, the most recent thing that I've read, at least, is that nothing really happened. That doesn't mean there's no black hole there. It just means that what they thought was going to happen with the gas cloud didn't happen in the way they thought. And the recent pictures show that the gas cloud was really kind of in two pieces, as opposed to one big gas cloud. And so they're still doing a lot of analysis on this. But I think that their hope that this would somehow show the structure of this central black hole, as I say, was kind of a flop. Now that may turn out not to be the case, but so far I haven't seen anything that says otherwise. So they didn't really get out of that experiment what they wanted. It was still very interesting, but it wasn't what they wanted to get. The other thing that is a way to detect black holes, especially the supermassive ones in the center of galaxies, is something called gravitational lensing. When you have a dense object, a black hole object, millions of solar masses, it produces a strong gravitational field. And the way light works in a gravitational, I just lost something. I don't know, did the sound go off all of a sudden?
Yeah.
I didn't do anything to it. Are we all right? I'll just talk loud. Okay, well, I'll talk loud. The light behind a galaxy that's between us and a bunch of other light, when it comes toward us, it gets bent around that massive object in the center of that galaxy. And so it creates these objects that look like rings around a galaxy. This is a galaxy behind this galaxy. And it creates this kind of ring, and all these ring structures, and there are lots of these when you look out with the Hubble or something else. And so you can, because of what's potentially producing this, you can calculate the mass of the black holes in the center of these galaxies and get a good idea. And that's one of the reasons why people know that there are lots of galaxies have these massive objects in the center, because the mass that's on the outside of the galaxy isn't nearly enough to do this lensing. So it has to be something in the center that's doing it. And so this is a really great way of looking for black holes in supermassive galaxies. All right, so the other interesting question that everybody always asks is, what happens when you fall into a black hole? Well, the famous word for that is spaghettification. And here are some images of spaghettification that I was able to get off the internet. Isaac Asimov has one in a book in 1978, this picture. And here's one by somebody else about spaghettification. And then somebody, I think a high school student, did this one in a flip book. And I thought that was about the best one. And so this is what's believed to happen if you were to fall into a black hole. Oops, didn't want to go back yet. Basically, the gravitational field of a black hole, of course, it gets stronger and stronger as you get closer and closer. So if you're falling down and you get close to a black hole that's pretty small in size, not small in mass, your feet are being pulled toward the center of the black hole more quickly and more strongly than your head is. And so your body is being pulled this way. And the tidal lines of the gravitational field also start to come in like this. So you're going to be squished in and pulled out. And there's the spaghettification. Okay. Now, of course, no one's seen this happen except in science fiction films. But this is what will surely happen in any strong gravitational field, even like a neutron star. You'll have this kind of tidal forces doing this structure. Now, this won't necessarily happen for all black holes, at least not like this amazing. A small black hole or a stellar-sized black hole, yes, the gravitational field as you get toward the horizon of the black hole is very, very strong. But for a supermassive black hole, the horizon is very far away, relatively speaking, and the gravitational field at the horizon of the black hole is very weak. So you could be falling toward the black hole and go right through the horizon of the black hole, be unable to get back out again, and not even know it until you realized you couldn't go that direction anymore. And it wouldn't be until much later, maybe seconds, but maybe minutes later, that just spaghettification would occur, and you'd be ripped to shreds. Furthermore, somebody watching you do this far out wouldn't see this happening at all, because the closer you get to a black hole, the more the light that's coming from you is redshifted, and so the weaker it gets. And so a person far away will just see you kind of fade out. They won't ever see you disappear, They'll just see you fade away and then nothing. But the nothing will occur. They could look 100 years later and still might see photons of you from you coming out if you were shining a flashlight or something, but highly, highly redshifted coming out if you had a way to measure that. So you're never, somebody from the outside is never going to see somebody falling into a black hole. They'll just see this kind of weakening of the light that's coming from you. You'll be gone, long gone, but they won't see you that way. Okay. Now, of course, the other famous thing about black holes is the notion of wormholes, which is, of course, the big thing in science fiction. And the original name for these was Einstein-Rosen bridges. But back in 1935, when Einstein and Rosen wrote papers on this, they weren't named wormholes until Johnny Wheeler came along and named them wormholes like he named black holes. He was very good at naming things in very clever ways. And the notion was an Einstein-Rosen bridge is that you have a black hole-like object on one side here in the universe, and then another one on another side of the universe, and the distance between here and here, it can be very small, but the distance between here around here in the universe can be very large. This could be, I don't know, 100 feet or miles or something like this, and this could be light years. Okay. Now, no one's ever seen a wormhole. The notion that wormholes can even exist is very questionable because partly they might form, but the instant you try to go into one, the perturbations of you going into it would change the gravitational field just enough to cause the tunnel to collapse. So you have to feed it negative energy or exotic matter or something to keep it open long enough for something to get through. And if it was big enough, you could conceivably get something through. You could send a signal through, something like that. The instant you're able to do this, then weird stuff starts to happen. You can start creating time machines, all kind of other strange things that seem to violate a lot of physical laws. Well, Kip Thorne wrote some really good books, and I'll show you a picture of that later about that. He was the guy who helped Carl Sagan come together with the book called Contact, which was made into a movie back in '85. And so this is, Kip was also a student of John Wheeler, just like Feynman and others were, and Misner and whatnot. And then Kip is one of the producers of the movie Interstellar, which I highly recommend to go see if you get a chance. And these are some of the images from Interstellar. And these are ray traces about what would happen if you were to look at a black hole close up. What would the light around it look like? And it would make these very strange structures around the black hole. And they actually did calculate real physics calculations for this movie to show what a black hole would really look like in certain circumstances. So that's, Kip is very, very clever at, like his teacher Wheeler, at putting things into words and into pictures. So if you haven't seen that movie, I recommend it. And there's one of the things from the movie. Okay, now we're coming to what the things I'm working on right now, and also being done in Chapel Hill, is to try to decide, are black holes really black? And do they even exist? And the answers to that are no, black holes are not really black. They may not even be holes in some sense. And do they really exist? Well, sort of, but maybe not in the way that they're standardly defined. So if and I'm going to just read this, if by black you mean you cannot see anything coming from an isolated black hole, then it's not black. Hawking radiation will always come off. So if you mean by black, there's nothing coming off of it, that's not true. Because if you carefully look at a black hole and you believe in Hawking radiation, there's always going to be something coming off of it that's measurable. It might be incredibly weak, depending on the size of the black hole, but you should be able to see it. If by black you mean that nothing can ever get out, then no, they're not black. In a purely mathematical black hole, nothing can get out. But in a real black hole, in some sense, in the universe, there's no such thing as this horizon that occurs. It's that's a mathematical construct. There's other things that are called trapped surfaces, which for a time keep things from coming out, or apparent horizons, that sort of thing. But ultimately, if you wait long enough, stuff can get back out. In fact, stuff has to get back out or quantum mechanics is wrong. So they're not black.
Question is, what a limitation on what the size of black holes is the Planck size versus the minimum size anything could be?
Yes. The Planck mass of the Planck size, 10 to the minus 34 centimeters, I believe. So yes, that's where everything breaks down. Where you need a quantum theory of gravity at that point, and that doesn't exist. No one has any idea how to do that. String theory doesn't do that. Loop quantum gravity doesn't do that. None of them can do that yet, and we don't have any idea how. And we need a lot more physics and mathematics to do that. Okay?
On your graph up there, some of your words are in purple color. If that's on internet or something, is that a link to something else or more?
No. That's just emphasis. There's no links. The other thing is that because in the mathematical structures of black holes at the center, whether they're rotating or not, there are infinite densities. There's no infinities in the universe. That doesn't make any sense. So you have to come up with theories that get rid of those infinities. And we don't know how to do that either. But that's what we're working on right now. Well, first of all, we don't have a quantum theory of gravity. So we're trying to make models that will show somehow that the singularities, these infinite areas, don't occur. And if they don't occur, then they're not black holes. They're something else, but they're not black holes. And the key word in that is back reaction. Remember I said that matter affects gravity and gravity affects matter. So what we're working on now is taking models of black holes, or black hole-like objects, or stars that are falling into black holes, and see what happens as they collapse, giving off Hawking radiation at the same time, so putting some quantum mechanics in. And that Hawking radiation affects the matter as it goes in, changes the density, changes the pressure, changes how the object will collapse, so we can call it a black hole. And so that's a back reaction problem. And the numerical simulations that we've done so far, and this has been done primarily by Laura Massini-Houghton in Chapel Hill, is that at some point, if you take quantum mechanics into effect, it'll reach a point where it'll bounce before the singularity occurs, before the horizon occurs, that there'll be a kind of a bounce in the star. And so the black hole, in the traditional sense, will not be formed. That doesn't mean a really dense object won't be formed, an object that looks like a black hole, but it won't be black, it won't be a hole, it won't be a mathematical black hole, it'll be some other kind of object that looks like a black hole. And so that's the thing that we're all working on right now, is to do the models of these as best we can to figure out just how this back reaction occurs, to see what really does end up. If it's not a black hole, what is it? And what does it look like when it happens? Does it give off a particular kind of radiation that we might measure? And so that's the heavy research in black holes in the theoretical side is being done with this research right now. Yeah.
The Hawking radiation, is that constant, or does that tend to increase?
It increases as
is
yes.
it an exponential increase, or is it as?
I guess really sort of it is, but it's proportional to 1 over the mass or something like that.
Right.
Okay, so it's inversely proportional to the mass, and so as the mass gets smaller, the temperature of the black hole, which means the amount of radiation gets higher. Okay, and so that's and that just means more back reaction effect as you go on. Well, it's in the traditional Hawking radiation, it's black body radiation, so it has the same sort of Planckian curve that black body radiation has. Okay, but that curve moves up in the spectrum and gets higher and higher energy as the mass of the black hole gets smaller and the temperature gets higher. So it's basically black body. unless you start putting things like rotation and other stuff into it, which will change the spectrum. The simplest form is just a straight plunk-in spectrum, you know, like heating up a piece of metal or something would do. Okay, so that's kind of where things are now. It's certainly where I am right now in this kind of work. So to finish off, I want to give some pointers to some books if you're interested in this subject. And these are various levels of books. The popular level books are Lenny Suskind's book, The Black Hole War, which talks about his work with and against Hawking. Neil deGrasse Tyson's book, Death by Black Hole. The classic sort of textbook for gravitation is Misner, Thorne, and Wheeler, which has been around for many, many years, but still is classic. Then there's Kip's book on black holes and time warps, which is fantastic. A little more technical than this is technical book. These are popular level books. This is a popular level book, Scharf's book. Kip's book is a little more technical, but more detailed and probably a bit more accurate than these others are. There's the old lectures that Feynman gave on gravitation, which are still relevant, because it's Feynman and he's just brilliant at putting this stuff together. There's Kip's book, which goes along with the movie Interstellar, which I highly recommend. If you haven't seen the movie, see the movie, buy the book, and read the book, and go back to see the movie again, because you'll like it better the second time around. I did that, and it's even more so. Then his book that I edited, it was my mentor's lectures on gravitation. This one I say, unless you're really nuts and want to learn really deep stuff, stay away from that. But it's an amazing book. It's just incredibly technical. And I spent 2 years converting his lecture notes into this book. And it was a lot of fun, but you really have to be serious to get that book. If somebody wants to see it, I'll show you a copy sometime. Anyway, so then if you go to YouTube and just type black hole in, you'll find all kinds of really good lectures by some of these people like Susskind on black holes that are really, really great. Wikipedia, of course, has lots and lots of articles on these things that you can read too. And if you just go to a bookstore and look through the physics section, you'll find a lot of really good books on this subject as well, both gravitation and quantum theory and black holes and everything else.
For the mathematical challenge.
Yeah.
Is Kip Thorne? I'm reading the Science of Interstellar right now.
Yeah.
He has a good approach to explaining things. Is he one of the better guys for people who?
He's the best guy.
Theoretical.
Best.
Okay.
I would say Kip's the best.
Okay. If someone's interested, but they don't want to get into all the.
Yeah, I think that's a really good book to start off, even if you haven't seen the movie.
Right.
That's a really good book to start out with. Yeah. Okay. Unless there are any questions, I'm finished.
Just want to remind folks we're still streaming this, so for the people or the video, we want to hear your voice. Please wait for the microphone if you've got questions.
Mike, can we turn up the lights? That's
And Brian's got a microphone as well, so.
wrong way. There you go. Good. That's good. Now I can see it. Okay. Questions? Anybody got questions?
So I'm clearly not a scientist, but I'm interested in sort of the personal aspect. You're a theoretician,
Yeah.
I take it. So early on, black holes were only a theory. And there was, at some point, I don't know, you described it here in the 70s and 60s, where they discovered the first
Yes.
of this sort.
Yeah.
What was that like in the scientific community? I mean, was that amazing or what?
Yeah, for us, it was in particular Roy Kerr's discovery of the Kerr solution, the rotating black hole thing, was amazing. Everybody was talking about that. I was still in high school at the time, but even I heard about it in a little town in Illinois. I heard about it because this was a big deal. So a lot of general relativity up to that point was trying to find these solutions of Einstein's equations, because it was really hard, and there were only a few. Okay, when Kerr came along with that solution, because it looked like it was possible to apply that to the real world, where previous solutions were solutions about entire universes or really, really simple things like the Schwarzschild black holes, which we knew weren't physically in the real universe likely. When that solution came along, it just caused a revolution in people analyzing that. And then people generalized that. They added electric fields, they added magnetic fields, they added all kinds of things. And so there were lots of other kinds of solutions that came along using his techniques, which now, as I said, can be done on a computer easily. But back then, wow, you're too close. Sorry about that. But yeah, no, it was a big deal. And the Hawking stuff back in the 70s was a big deal too, just because it gave us some mechanism for trying to get general relativity and quantum mechanics together in some fashion, because there had been no good success in that, and there was nothing that you could potentially test. So, okay, I'm back again. Okay.
Steve, earlier you mentioned, I think it was Hawking and was it Rosen?
No, Einstein and Rosen did the wormholes.
Yeah, no, it was Hawking.
Hawking, Bekenstein, and Parker.
Yeah. I think it was when you're talking about all objects will collapse into.
Oh, Penrose. Yeah, Penrose. Sure.
They'll all collapse into a singularity.
Of some sort. Yes.
Of some sort. So how does that necessarily then relate to, let's say, a star like our own sun? When it does collapse, it will not form a black hole in the way we understand it.
No, that's right. I should have said objects of a certain size, beyond a certain size, will collapse into black holes, or some form of ultra-dense object like that. Okay, our sun won't do that. It'll go down to a white dwarf or something and die out.
Well, here's something. What is your feeling on the current universe Big Bang theory, that this is just another universe?
The multiverse stuff. Well, that's a whole other lecture.
Yeah, but I mean,
I can do that down the road, but I haven't got one of those prepared. But yeah, there are lots of different multiverses. Okay, read Brian Green's book. Brian Green. Yeah, he has. Look up Brian Green. He's at Columbia. He has 3 books out, all of which are excellent. His third one, most recent one, is on multiverse stuff, and that's a really interesting one. But look up multiverse on the web, and there are lots of articles on it, and they talk about different things. There are lots of different kinds of multiverse, and multiverses for different reasons, and so there's no one theory of that. Frank?
I know somebody just mentioned Big Bang, which brought up something that was interesting that someone asked at an Asheville Astronomy Club meeting, and that is, what was here before the Big Bang?
Depends on who you talk to.
My theory would be you would have to go all the way back to Genesis chapter 1, verse 1, then modify. In the beginning, God created the Big Bang, which created all the heavens and the earth, and it was good.
That's one way to look at it. Roger Penrose says that there's a cyclic universe that never stopped. It do the Big Bang, Big Crunch, Big Bang, Big Crunch. There's lots of different ways of looking at it.
In reference to the wormhole idea, I mean, the way I'm viewing a black hole is not really a hole, it's more like a black sphere. There's something coming more to it. How are you getting something from a sphere to a tunnel between the two?
It's a different solution of Einstein's equations. It's the Schwarzschild solution is one that just represents a point mass with a horizon around it. The Einstein-Rosen solution is a different solution of Einstein's equations that has basically 2 holes connected. So it's just a geometry thing. It's just a sheet with a hole connected between them, and you can make a sheet that has multiple wormholes in it if you want to.
So it's kind of visual idea. When something like a sphere, I'm not saying it's symmetric, but you have 2 here. I was trying to visualize how you get a sphere falling internal into the sphere. The 2 different.
Yeah, it's not. Well, it's just that each side is not really a black hole. Okay, it's a wormhole. It's a totally different solution of Einstein's equations. So when you're falling in, I mean, it doesn't mean that you can get out. When you go into one side, you're almost guaranteed to have to go either to be crunched in the center of it if it collapses on you, or go through the other side. But you're not going to come back out the other way. It's a one-way thing. You get to the other side, you might be able to go back through the other way. but it all has to do with something called geodesics, and you take a point in one part of the space and a point in another part of the space and find out what the path is between those in the gravitational field. And in the wormhole space, the geodesics that go through the center of the wormhole are one kind. Okay, the geodesics that go away from the wormhole in space are of another kind. I mean, the Raychaudhuri equation is partly that. It helps you to discover how particles go from one place to another, and along what path.
Steve, near the end of your talk tonight,
Yeah.
You're describing the actual instance of what a black hole might look like.
Yeah.
And I was just wondering if, I mean, it's really, I think, quite intriguing that what we're actually seeing in nature may not exactly be the way we modeled it. Could you elaborate just a little more on what the actual instance of a black hole might look like and how it might behave, and how is that different from the actual modeling?
The way the black hole, okay, there's two ways to look at this. There's these mathematical black holes, and then there's physical black holes. And the mathematics of it is just a model of the physical one, and not a perfect model. Okay, so over here you've got an object that's incredibly dense, may or may not, certainly does not have a singularity like the mathematical model has, because that just doesn't make sense. But we don't know yet how to solve that problem. May have a horizon, but probably not like the mathematical one. It has something like a horizon, but that horizon is changing in structure. Mostly over here you'll have not a lot of matter around or anything. It's just a mathematics, because that's hard to do. But over here you're going to have mostly, like, you have matter going around it, especially if it's rotating. If it has a magnetic field, if it has a charge, it's a much more complicated object. And so what you really now, what we see mostly is supermassive black holes where there's not a lot of big accretion disks or anything around it, but you're seeing things orbiting it, so you can figure out that it's a black hole, or at least a very dense object. Or you see regular black holes that are in a system with another star that is accreting matter from that other star and creating this disk, and that rotation and the banging around of the matter causes a lot of energy to come off. And that can be predicted very, very well. And so we see that in the Chandra telescope and other things. And so that's the kind of thing you're looking at. But there are no perfect mathematical models to these things. Ultimately, it becomes computer simulations, like I showed. And hopefully those are close enough to what we're really seeing. Okay. And as we learn more, those will get better.
How can wormholes form with an expanding universe? That's sure. You may have
These days, the notion of any kind of wormholes forming have more to do with tiny wormholes that aren't, one wormhole on one side of the universe and one hole on the other side of the universe, but little ones that just sort of go back down again. The notion that any real wormhole exists is pretty unlikely. And if you read Kip's book or other books, they talk about why that's unlikely. And partly, if you were able to create a wormhole, some advanced civilization would be able to create one. And suppose you could create one in a lab, and you can move it around, move the ends of it around. You could keep one in your lab and move the other to some other place in the universe, and you would be able to travel then. I mean, somebody would have to do it. They'd have to make the initial, fly the other thing a light year away. And then the person on the lab could get into that wormhole if you could keep it stable and go a light year away without actually having to do that travel. Okay, but how to keep a wormhole stable like that, because they're really unstable, at least the current models. So the instant you throw any kind of matter into a wormhole, it destabilizes it and just crunches off, and it just becomes two black holes or something, or two ends of a wormhole, whatever that is. And so it's unlikely there are any wormholes unless maybe ultra microscopic ones that only exist for a short time and then go away for a very short time, and those aren't useful for anything. You can't be able to travel through them. Now, whether something like that could have happened at the very beginning of the universe, I don't think anybody knows. I think they're so unstable that in the very beginning of the universe was a pretty unstable place it's unlikely they would have survived even if they had been created. But I don't think anybody really knows. I mean, we know little enough about black holes still, much less wormholes, which were way more complicated. So maybe down the road we'll know. But something else?
I had a question about Hawking radiation that slowly leaks out of a black hole. But as long as a black hole is surrounded by undigested mass, would a similar phenomenon counteract that sense?
Sure. Yeah, I mean, you could have a black hole. Well, a typical size black hole, like 10 solar masses or something like that, is going to give up very, very little Hawking radiation, barely measurable. So anything you're going to see is a matter of accreting into the black hole or going around the black hole. It's going to dominate. It's only if you have, generally speaking, if you're really tiny black holes, that the Hawking radiation is going to become easily evident. That doesn't mean it's not important. It's just that's when it's evident. Okay, and so any matter around the black hole, it's going to really dominate over Hawking radiation. Yeah.
We got one more question.
You mentioned some of the experiments that are ongoing that
Yes.
have yet to produce results.
Yes.
Of those, which one would you like to have results and why?
The gravitational radiation ones.
And why?
Because that's one of the main predictions of Einstein's theory that has not yet been fully tested, and that will be an amazing thing. If the LIGO experiments can really show gravitational radiation from something, and it matches with Einstein's theory, that's going to be huge. There was some notion recently that they detected gravitational radiation effects at the beginning of the universe. There was a couple of months back, there was a bunch of hoopla about that this had proven that the inflationary model of the universe was correct, and that Andre Lindy and Alan Guth and these guys who did that were going to get the Nobel Prize right away, and then it turned out to be wrong. Okay, so that was because that was gravitational radiation, but that was gravitational radiation from the beginning of the universe, as opposed to something coming from rotating neutron stars or colliding black holes or something like that, which is more likely to be found. But these, like I said, these things, just eliminating the noise from these experiments is so difficult that you really have to run these experiments for years and take data for years and then analyze those things. It's like the LHC, where you have to take trillions and trillions of gigabytes of data in order to find the Higgs boson. It's just really, really hard experiments to do, and big and expensive and all of that. Expensive is the worst thing, of course, nowadays. But yeah, I think for me, gravitational radiation would be the big deal. Or maybe even something falling into the central black hole of our galaxy would be interesting too. There are lots of things, lots of cool things to look forward to.
I think that pretty much finishes up. Thanks everybody for all the great questions, and thanks Steve for coming out tonight. Really enjoyed the talk.